Okay, so you're saying the question basically is that Bell's inequalities classically derived. Why am I using them with quantum systems and showing violation? Okay, Bell's inequalities are a great tool in order to distinguish between quantum and classical correlation. So all classical correlations satisfy Bell's inequalities, and the fact that quantum mechanics doesn't satisfy them means there's non-classical correlation there, and they're used as a way to measure the difference between quantum and classical correlation. Yeah, in my model, that's what I tried to say at the beginning. There's nothing classical about what I'm doing. My model is 100% quantum. I haven't got anything classical. I just use quantum ideas. This is one of the misconceptions, as I mentioned at the beginning, of people thinking that local realistic models are classical. Not at all. Locality, we know what that is. Reality means pure states, pure dispersion-free states. Nothing more. It doesn't mean classical states. And this is only for spin. I mean, I haven't done it for position and momentum. But, I mean, I'm just using quantum ideas and nothing else in my model. And that's why it works. And the correlations that I get out of my model violate Bell's inequalities, which means I've got that extra correlation in with my model. If you do a calculation with a spin model, you'll still get violations. No, you have to use entangled. You have to use two spins which are entangled. Yeah, and you have to assume that entanglement works when they're separated. The entanglement is assumed to persist to the other ends. How? Nobody knows. That's quantum weirdness. Initially they're correlated, like mine are, and the correlation remains as you separate them. When you filter them, the correlation is the same in others, but it comes out in a different angle because the angles are chosen different, and so that's where you get the cosine theta between them. But it's a purely quantum mechanical description. Anybody else? Yes. Theo. That's right. So the question is that, you know, you have isotropic system and the spin is in its two-dimensional system and you have that √2 spin which exists that way. How strong a field do you need to add in order to make that spin stand up? I think it is tiny because I think the fields around a single spin are minute. So any small field you put on, it'll get to the maximum spin immediately. I don't think we could use a magnetic field which has a magnetic moment which is less than the magnetic moment of an electron. I don't know if somebody, experimentalists, know if you could. But I think as that spin sees the magnetic field, it pops up and takes notice. And it's at its maximum precession. Say that again? If you had a nano machine with a little magnetic field in it, I don't think we could create a magnetic field which is weak enough to see what happened to that spin. I think it quickly mutates and lines up in the direction of the magnetic field, which is what we see. What happens in that intervening period, when I went through the calculation by Scully et al. 1969, where they pass a spin through a Stern-Gerlach filter, when I pass my two-dimensional spin through the Stern-Gerlach filter, I get exactly the same equations. And what Scully says is one component lines up, gets a torque and lines up with the field, and the other states precess and average away in the XY plane, which is exactly what I see. I don't think you can get a weak enough field. I don't think you can measure that √2 spin with a magnetic field. If you took a magnetic field and you lined it directly along, and you had them all polarized in that direction, I think they would start to wobble and mutate and then fall one way or the other. And if you change that isotropy, then one axis lines up and the other is averaged away. That's what the calculations show, and it makes physical sense. So when you turn on the field, the spin sits up and takes notice. And that's what we see. You see, if you use the Dirac equation, you go into quantum field theory, you look at the Dirac equation, you have to have a probe. If you don't have a probe, you don't get spin. I don't think quantum field theory is going to be able to get this model out. Maybe, I hope it can, but the Dirac equation needs a probe. But the algebra of sigma x, y, and z, the Lie algebra SU2 of the spin, is fundamental, but I haven't changed that algebra. All I've done is multiply one component by an I. And that's all I've done. Sigma x plus I sigma y. You know, why not? Nobody can say it's wrong. How anybody can say that choosing sigma x, y, and z is any better than choosing sigma x, z, and I sigma y? In the same set of operators, I'm using the same algebra of operators, I'm using the same Lie algebra. So, what's the problem? It's your choice, Occam's razor. It's your choice. And I chose that, And at first I thought he was crazy because fundamentally the states are non-Hermitian. But then when you work it out, everything becomes Hermitian. And there's another thing I didn't mention. The entangled singlet state separates into a product using those states. It's the mathematical identity. They separate out. So entanglement, as I said, is a property of quantum mechanics but not of nature. And with its two-dimensional spin, you can make the singlet state separable. I didn't want to mention that, but it is one of the extra things that helps see that it sort of makes sense. He's asking about entanglement separated. I'm saying they're not. It was 1997, and I was in India, and I was moonstruck. Actually, it was a side effect from my malaria pills. And I said to myself, I started to read about, quantum computing, and I got into Bell's theorem, and I said, it makes no sense. How can entanglement separate to space-like separations, to different light cones? What is it? Nikolai Gizen does experiments between little Swiss villages 10 miles apart, actually through 21 kilometers of fiber optics. And he calculated the time it takes for the spins to flip and flop. And his answer is the connectivity between the two exceeds 10 million times the speed of light. And he concluded that quantum mechanics was complete, but relativity was incomplete. Clauser said, of the Clauser-Hahn-Shimoni-Hall CHS form of Bell's inequalities, Clauser said, quantum mechanics and relativity live in peaceful coexistence. It's to placate, because nobody understands what's going on. Yes, David? No information gets passed, and then you have the non-cloning theorem and all that stuff, which is all. I'm saying is that non-locality makes no sense. It makes no physical sense. Quantum weirdness makes no sense. And therefore there should be, if nature is logical, there must be an explanation, and this is my explanation. And it seems to work, and it seems to be consistent. The surprise is that you don't get 2 root 2 in one experiment because of the CHS forms not being classical and not taking into account commutation. But apart from that, I think it's a very simple thing to do, and it works out. I don't see any loose ends. If people see loose ends, please let me know so I can tie them up, or try. Anyway, yes. Bell's inequalities are derived classically from a few assumptions, reasonable assumptions. People have tried to assail them, but they've stood the test of time since 1964. And people like to say maybe there's a contextual approach in understanding this correlation, but Bell's inequalities seem to have stood the test of time and are a measure of classical correlation, and all classical events that have ever been compared satisfy Bell's inequalities, and quantum mechanics doesn't. Why? Because of quantum correlation. Where does that come from? Entanglement or my root 2 spin? It's one or the other at this point. I hope so. The spin 1/2 is the simplest system. It's got 2 states. There must be a way to do it for position and momentum to resolve that aspect. I've not pursued it. I had enough trouble getting this to work with 2 states and 4 states. I don't know what it's like when you have an infinite number. But I would imagine that there is a way of doing it, but that's down the road. I haven't got it published. In 2009, I became blacklisted on the Quantum Archives. I submitted a paper to Physical Review Letter in which I questioned non-locality. The editor, Garisto, replied to me, our editorial policy is to reject any paper without that questions the veracity of non-locality. There is a quantum crackpot challenge. They will pillarize you if you go and say quantum mechanics is incomplete. So resistance, many things rest upon that. And if it's wrong, you've got to rethink the whole thing. And if quantum mechanics is incomplete, you've got to write the textbooks. So yes, the resistance is enormous. So I blog. So, well, thank you very much for your attention.